Welcome back, Trinity. We're going to start with a review of electron configuration. You'll need to get out a piece of paper and take some notes on this. I'll be looking for them when you return to school. So, as a reminder, electron configuration just tells you where the electrons are in relationship to the nucleus of the atoms. So, here's our key. I've done silicon for you, the electron configuration of that. We're going to go through and look at that individually. But remember, as a key, we have energy levels. These are distances from the nucleus. So energy level 1 is closest to the nucleus, and then you move out a little bit further and you'll get energy level 2, 3. There are 7 different energy levels that are available for the atoms. Within each energy level, we have another organization system called subshells. And we give those letters. Those are S, P, D, and F. This little line here represents the orbital. So remember, the orbital is the shape of the subshell. So S is shaped a sphere, and there will only be one orbital in S. So an orbital is just like the shape in which the electrons can travel. So when you're in an S subshell, you're a sphere. P looks like a dumbbell, so remember that there are 3 orbitals in there, and then they have to do with 3-dimensional space. So you'll have one dumbbell shape that's oriented in the x-axis, another oriented in the y-axis, and a third oriented in the z-axis. And then when you're drawing the arrows, each arrow indicates an electron. They will pair up. This would indicate that we have 2 electrons here. And the reason why we use up and down arrows is that indicates a spin. Remember, when they're ever together in a pair, they will always have opposite spin. And that's why we use up and down arrows. So if we want to look at silicon individually, you're going to find silicon in your periodic table, and you're going to find out how many electrons it has. So you'll have to go to a periodic table. You'll locate silicon, which is right here. And you'll note that it has 14 electrons. If we want to do the electron configuration, there's 3 different ways that we can do it or show it. The first one, we're going to look at the long way. This gives you a little bit more information. It's more visual, and it shows you orbitals and it shows you spin. So this is a really great way to understand what we're doing here. We'll start in energy level 1. Energy level 1 has an S subshell, which has 1 orbital. Okay, and that can hold 2 electrons. So we'll fill up the first 2 electrons there. Energy level 1 is now full. So now we move out to energy level 2. Energy level 2 has an S subshell and a P subshell. So remember, S is a spherical shape. And so there is only 1 orbital there. 2 electrons will go there. When you get to the P, remember these are dumbbell shape. This would represent PX, PY, PZ. Notice that no matter where we're at, each orbital can only hold a maximum of 2 electrons. Okay. Once 2 is filled up, we go to energy level 3 and we start filling in the electrons there. 3S will have 2, and then 3P will have 1 in PX and 1 electron in PY. We have 14 electrons. We've got 2, 4, 6, 8, 10, 12, 13, 14. We've showed where all the electrons are in relation to the nucleus. I did put a box around our valence electrons there. So remember, valence electrons are the electrons in the outermost energy level. The outermost energy level here is 3, because energy levels are 1, 2, 3. So it'd be all the electrons within the 3rd energy level. And we have 4, 1, 2, 3, 4. 4 valence. Now, we can write it out like that, which is great for something that doesn't have a lot of electrons. But when you get into these elements that have 58, 59, 80 electrons, this would be very time consuming to do. So we have a couple different ways that we handle that. Instead of writing it out like this, we could use our shortcut method. So remember, when we do this, we just write from left to right. In place of the arrows, we're going to use superscripts. So 1S, these 2 arrows would represent that number 2. So this would be 2 electrons, okay? So 1s2, 2s2, 2p6. Notice again, if I go back and count my electrons, 2, 4, 10, 12, 14. I have 14. I put a box around my valence electrons. So again, remember these are equivalent. They're the same thing. They're just two different ways of showing that. We even have an easier way to show that. Whenever you're looking at your shortcut method, whatever is not valence will always represent a noble gas. Okay, so again, whatever is not valence will always represent a noble gas. So what we can do is we can use our noble gas configuration. We take the ones that are not valence, we count our electrons, 2, 4, 10, and we figure out which noble gas that is. When you look at your periodic table, remember these are your noble gases. 10 is neon. So instead of writing all of this, we can shorten our work by saying, well, that represents neon. So I'll just write neon and then my valence. Now I still have 14 electrons. There are 10 there, 11, 12, 13, 14. So all three of these are ways to represent silicon's electron configuration. And then we learned how to do this loose dot diagram, which is just a real visual way of showing valence electrons. And so the rules there were, write the symbol for the element, Si, and then we'll use dots to represent the valence electrons. We have 4 valence electrons, so that would represent 1, 2, 3, 4. So that was your electron configuration. Now, the only other thing is you really have to think three-dimensionally here, which is hard to do sometimes. So I'm going to refer back to this. Okay, this is actually a diagram for neon. Okay, neon has 10 electrons total. And so this is a really good visualization. You'll have to visualize that the nucleus would be in the center of this image here. And then I want you to find the dark blue circle in the middle. That represents 1s. Remember, S is a sphere. And then I want you to find the larger circle outside of that. That represents 2s. And remember, S is a sphere. So in 1s, there are 2 electrons in that area, and they're moving around. We can't predict how they're moving, but they're moving. In that 2s area, there's 2 electrons, and they're moving around, okay? Those are orbitals that they're in. Then notice that you have a 2px, a 2py, and a 2pz. So locate those. They're shaped like dumbbells. And in each one of those, we have 2 electrons that are moving in that area. Okay, those are orbitals again. Px is an orbital, Py is an orbital, Pz is an orbital. Okay, that's the picture you have to have in your mind. Okay, moving on. That's old stuff. Now we're going to move on to new stuff. So this is going to be very familiar because we're going to continue with the development of the periodic table. Like, how did we get the periodic table that we have today? Who were some of the people that were involved in determining that and setting that up for us? We're going to start with, I'll tell you what, let's give ourselves a title here. Call it Development of the Periodic Table. Okay. We're going to start with a guy who's not actually represented in our current textbook, but he's kind of interesting, and so we're going to go ahead and learn about him. We're going to only learn 3 people. Okay, there were a lot more people that were involved in this, but these are the 3 that you have to know for sure. This guy's name is Dobriner. Okay, he is a German chemist. The year is 1829. He starts looking at the known elements, the ones that are known at that time, and he starts trying to figure out how can I put them in some kind of useful format so people can use them easily, where they make some sense. Okay, so what he starts doing is he starts trying to put them in groups. And he is putting them in groups of 3. Okay, so he places some elements in groups of 3. And those are going to be called triads. Tri meaning 3. Groups of 3 or triads. Now, when he places these particular elements in groups of 3, he sees some repeating properties. Or he sees properties that are changing in very predictable ways. So when he does this, what he notices is that the ones that he puts in groups of 3, he puts them there because they have similar chemical properties. In other words, they're either, the 3 that he puts in that group are either highly reactive or they're very stable. That would be an example of a chemical property. Okay, they either are going to combine with other elements, or they're going to blow up, or they're going to catch on fire, or they're just going to be happy the way they are. And so he's going to put them in groups where they have similar chemical properties with each other. And when he does that, what he finds out is they also have physical properties that vary in very predictable ways. Okay, so he was kind of onto something here. He thinks, you know, I can put these elements where they have similar properties, and that's how it's done today. Not the way he did it, but we'll bounce on this idea and take this to a whole nother level here when we get to some of these other chemists. But here's an example of one of his triads. He did a halogen triad. So remember, halogens are now called group 17, and there are more than 3 of them. But in 1829, he grouped 3 elements together. And the ones that he grouped were chlorine, bromine, and iodide. Okay. And if you look at this table right here, you can see that when you look at the properties, and these are all physical properties here, that they vary in a very specific way. In other words, you'll get your lowest amount or your lowest number with chlorine and the highest with iodide. Okay. So that's an example of what Dobriner did. Okay. Now, the next guy that we're going to learn about is Mendeleev. So, number 2. He's Russian. And there were about, I think there were about 60 known elements at this time. And he's looking again at a way to organize them in a way that's going to be useful for people. Same thing as Dobriner. Okay. What he starts doing is he takes all the known elements and he puts them on like little index cards. And he starts trying to place them in orders that make sense, where he can see trends, where he can see similarities, like Dobriner did. Okay. And as he starts trying to get a system going for his periodic table, he starts looking at atomic mass. So one of the properties that were known in Mendeleev's time, let's put a date on him, 1869. One of the properties that were known at this time was the atomic mass. So he starts arranging by atomic mass. Let's say by increasing atomic mass. And what happened was he got this pattern that emerged, and it was periodic. So what happened was after every 7 elements, he found that properties repeated. So a periodic pattern emerged. Properties repeated. every 7 elements. Today we know that there's actually every 8 elements. This periodic pattern still applies today, but it's every 8 elements because in his day in 1869, the noble gases had not been found yet. We didn't know about them. So there were no noble gases on his periodic table. One of the kind of interesting things that he did was he could predict once he started getting all his cards in place, because remember, he was using like index cards and stuff, and he was arranging these index cards based on properties and atomic masses. He could figure out where there were elements that had not yet been discovered, and he would just leave blank spaces in his periodic table and say, well, I believe that there's an element that should go here and we haven't discovered it yet. So he left blank spaces for undiscovered elements. And he also predicted their properties, okay, of those elements. Let's go ahead and write that one down. He predicted properties of the undiscovered elements. There is a picture in your textbook of Mendeleev's periodic table. You all have to, I'm going to ask you to go back and do some reading. And when you do that, you'll see his periodic table. It looks different than the one we have today. But I do want you to stop and take a look at it and see how it's different from the one that we have today and how it's the same. The third person that we're going to take notes on is Moseley. Okay, so we're up to like 1913 now in our time frame. So this all happens in a relatively close amount of time. He is English. He's a chemist. And he's looking at ways to better the periodic table that we currently have. And Mendeleev he was published and everything. So he got his periodic table published in scientific literature, and there's still work that's going on it, though, to make it even better. And so what Moseley does is he arranged, remember that Mendeleev arranged based on atomic mass. Moseley is going to change that, and he's going to base his arrangement on atomic number, which is the way we do it today. So let's say that he arranged a periodic table by increasing atomic number. Okay. Now he could do this because by this point in time we knew about protons, and so now we had an atomic number. Mendeleev did not have that information, so he couldn't, if he wanted to, he couldn't have arranged by atomic number because during his time that didn't exist. Okay, so we'll go ahead and say that he found that each element had a unique number of protons. He found that each element had a unique number of protons, which, remember, is our atomic number. Okay, that's the end of the notes that we're taking. There are some more things that you need to take care of that of those. So make sure that you go back and read your instructions for today. Hope you have a great day.